Okay.
All right. Good morning, everybody. Thank you for spending your Saturday working on physics. That's pretty amazing that you would do so. And I hope that this is helpful for you. And since we have a small group, and I want to make sure that I meet your needs as best as possible. If when we're going along you have a question, if you feel confident enough, just speak it out, okay? And so that I can hear your voice and ask your question. If you don't want to interrupt, or a little shy about speaking across, then just type it in the chat, and I will do my best to answer your questions. If I miss your question in the chat, just type it in again. All right, so let's get started. All right, our first session has to do with circular motion and gravity. Okay, now I want you to remember the biggest thing on the AP test is that they absolutely will be testing the idea of circular motion. Okay, so always keep an eye out for things that are changing direction. All right, they're going to give you a free response or multiple choice questions, and there's going to be an object that's changing direction. So just keep an eye out for that, because that's one of the things that students tend to miss on the test. When they're under stress, they forget, oh yeah, it's changing direction. So let's see what you know about acceleration. Okay, so here is our first poll. Let me see, can I Lou, do I have to? Oh, wait a minute. Launch polling. Oh, wait a minute. This is the whole poll. Wait a minute. We don't want to do that. Can we just launch them one at a time, Lou? Or is they all going to be launched at once?
I didn't realize it. It looks like they might all be at once, but I'm going to see if I can change that now. So let's just do that.
All right. Well, we'll just do this. We're going to play it by ear for a second here. So why don't we just do this in the chat? If you'll just type your letter answer while we're handling technical difficulties here. Is this object accelerating? We have a truck that's moving at 60 miles per hour when the driver hits the brakes. Now, is it accelerating? Yes. Is it a tangential acceleration? Is your answer yes? Is it centripetal acceleration? Is your answer yes? It has both tangential and centripetal. Or is it no? The object is not accelerating. All right, fantastic. I was hoping everybody would get this one right. The answer is yes, it has a tangential. Okay, so let's make sure we know the difference between these two. Tangential acceleration is acceleration tangent to your path. That means in the direction you're going. So that acceleration would be a change in speed kind of acceleration. And then you have centripetal acceleration, which is a change in direction type of acceleration. Okay, so make sure that you know the difference. All right, so here's our next one. Brian Vickers set the track speed record down here in Texas of 195 miles per hour in 2006 on Texas Motor Speedway. Assuming he traveled at a constant speed, where was he accelerating on the track? Was he accelerating in the front and the back stretches on the turns? Or there was no acceleration because his speed was constant? Or D, you're confused and you don't know? Type your answer in the chat. Okay, we got several B's, we got a few C's. All right, so this is a classic kind of trick question. All right, so I'm going to share my screen on this one so I can show you. So in a track like this, assuming it's an oval track, we've got some track that looks kind of like this. All right, now when the car is here and it's moving at a constant speed, then the acceleration will be 0 because there's no change in speed and there's no change in direction. Now, when you're around the turn, okay, your speed's staying the same, okay? But you are turning around the track, okay? Since you're turning around the track, you're going to have an acceleration, and the acceleration will be inward because you're changing direction. So you'll have a centripetal acceleration here, okay? Now, you can have both at the same time. So let's say that the cars started here, and this is where they begin. And let's say they start from rest, okay? And so from here to here, you're speeding up. And if you're speeding up, then you would have an acceleration in this direction, and that would be a tangential acceleration. Okay, if you're still speeding up as you're going around the turn, then you would have, say, if the car is here, you would still have a tangential acceleration because you're speeding up, but you would also have a centripetal acceleration towards the center. So you can have both at the same time, all right? So the net acceleration on the car in this turn would be this way for the tangential and this way for the centripetal. And then the total acceleration would be this. That would be the total acceleration, okay? So it's possible to have both at the same time, okay? An example of this is, say, like you take a baseball and you throw it into the air, right? And so its velocity is this way on its way up, okay? But the gravity force on the ball is this way, okay? So we know it's going to be accelerating downward. But if you think about it, that acceleration down is actually, there's a part of that acceleration that is perpendicular to the velocity and a part that is parallel to the velocity, okay? That's the centripetal part of the acceleration, and that's the tangential part of the acceleration, if that makes sense. So what you end up with is this part of the acceleration is causing the ball to turn, and this part of the acceleration is causing the ball to slow down because it's in the opposite direction of the velocity. Does that make sense? Okay. All right, so you can have both at the same time. Most of the problems on the AP test, you'll have one or the other, but there's usually one or two on the test where you might have both going on. All right, so just keep that in mind. All right, so the answer is on the turns if we're traveling at a constant speed. Okay, here we go. Assume that the dogs keep the tether cat moving at a constant speed. This is an old Gary Larson cartoon called Tether Cat, where they're playing tetherball with a cat. Now, the question is, if they keep the cat moving at a constant speed around the pole, do we have a tangential acceleration, centripetal acceleration, both, or neither? Ah, we have a poll. Awesome. You can answer the poll now.
Chris, I'm going to let you launch and unlaunch this poll. I'm going to see if I can create the other ones.
Okay, perfect. Thank you,
If
sir.
that's okay. Okay.
All right. Awesome. It looks like most of us. Okay, so when you're trying to decide whether it's accelerating, always ask yourself these two questions. Is it changing speed? Is it changing direction? Those are the two things, okay? So if it's changing speed, you have a tangential acceleration. If it's changing direction, then you have a centripetal acceleration, okay? So if the cat is moving at a constant speed, then we would not have a tangential acceleration. We would only have a centripetal acceleration because the cat is changing direction, all right? So the best answer is B, centripetal only, okay? All right, how about this one? A car speeds up while taking a left turn. Okay, so ask yourself the two questions. Is it changing direction? Centripetal. Is it speeding up or slowing down? Tangential. All right. There we go. Yeah, it has both. Okay, so now what's the direction of these forces? I'm sorry, what's the direction of these accelerations? Okay, so this car is moving, what, up, mostly upward. Okay, so its tangential acceleration would be in the upward direction. And then the centripetal acceleration would be towards the center of the circle. Okay, or the center of the arc that it's traveling through at that instant. Okay. All right. Oh, I didn't finish this slide. I was supposed to have arrows on here. So this was going to be our intro to the next questions, which was which way is the object accelerating? Okay, so I have a gecko that's sleeping. All right, so this one's pretty easy since I don't have any arrows on here. There's no direction. The gecko is not accelerating because it's just sitting still. So let's move on. All right, so for this one, so the person spins a bucket of water around her head at a constant rate. Okay, so now we're looking for the direction of the acceleration. So we're going one step further. Our first step was, is it accelerating? Okay, changing speed, changing direction. Now, which way is it accelerating? Oh, this is not. Let's end that one. That's not the one we want.
Wrong pole?
Yeah. There we go. Awesome. Okay, so which way is it accelerating? Okay. So let's see here. So we have our bucket of water here. Now, the bucket of water is going around in a circle. Now, it's said that it's a constant rate. If it has a constant rate, the tangential acceleration is 0. So it's not changing speed. But it is definitely changing direction. Therefore, we have to have a centripetal acceleration. Okay, so here's the deal. Which way is the centripetal acceleration? It's always towards the center of the circle. So you need to identify where the center of the circle is. Center of the circle is here. And so therefore, it's accelerating this way. Okay. Now, if the bucket was speeding up, say the bucket, I don't remember which way the bucket was going in the picture. Let's say the bucket's going this way. Then the tangential acceleration, this is kind of a 3D picture, so bear with me. The tangential acceleration, like the name implies, it's tangent to the path. So tangent acceleration, it's either going to be this way if you're speeding up, or it'll be this way if you slow down. Okay, that makes sense? So it's either in the direction you're going if you're speeding up, it's in the opposite direction you're going if you're slowing down, but centripetal is always towards the center, always, always. Okay? All right. So this one, the best answer is D, towards the center of the circle, because all we have is centripetal acceleration. All right. Now, how about this one? Which way is it accelerating? You have a Ferris wheel that rotates at a constant angular speed. Now, I don't know if you've gotten to that symbol yet, omega. You may not have in your class, okay? and that's okay. But omega means rotation, all right? And the omega is constant clockwise, so it's moving around at a constant rate. So which way is the that Ferris wheel car there that's on the far right? Which way is it accelerating? Is it to the left, to the right, straight down, or down and to the left? Okay. So let's see here. This one's a little tricky, but ask yourself the question. Is it changing speed? Is it getting faster or slower? And then is it changing direction? So here we go. Here it is. If it's moving around, which way was it going? This way? With a constant rotation, okay? And then it's definitely changing direction. So we have a centripetal acceleration towards the center, okay? Now, since it's rotating at a constant rate, so like if you were here on the end of this Ferris wheel and you're going around at a constant rate, then you have a constant speed, right? You're going around and around and around at a constant speed. So we have constant speed, therefore the tangential acceleration is 0. So there won't be any tangential. So it's just towards the center. So the best answer would be A. Okay. All right, how about this one? A roller coaster going over the top of a hill. Oops, let me relaunch this. Roller coaster going over the top of a hill. Which way is it accelerating? Okay. Now it's definitely changing direction, right? So that means we should have at least D downward. Now, the question is it speeding up or slowing down? So you know that the roller coaster on the way up the hill would be slowing down. And a roller coaster on the way down the hill would be speeding up. So therefore, if it's at the very top, then it should not be, it stopped slowing down, but hasn't started speeding up. So we should only have centripetal downward. D would be our best answer. Okay. All right. How about this one? You got a race car that's speeding up while traveling counterclockwise around a track. Which way is it accelerating? So is it changing direction? Yes. Is it changing speed? Yes. So we have both kinds of acceleration. So how do they add up? Hey, there we go. The best answer is B. The A arrow would represent the centripetal acceleration as it turns, and the C arrow would represent the tangential acceleration as it speeds up. And when you add vector A and C, you get vector B. Excellent. All right, how about this one? Okay, you've got a child
back and I can handle the polling.
What's that? What'd you say, Luke?
I'm back. I've created polls so I can handle the polling from here. I'm back and I've created polls for all the other questions, so I can handle it from. I'll take over for you here.
All right, thank you, sir.
You're doing great.
You're doing great too. You're great tech support. All right, we have a child that's swinging and on a swing. And so they're at the very bottom of the arc, okay? So they're going back and forth like a pendulum. So at the very bottom, which way are they accelerating? So are they changing direction? Yes, they are most definitely changing direction. So that means they have to have an acceleration upward. Okay. And at the bottom of the swing, at the very bottom of the swing, are they changing speed? Okay, so they're speeding up on the way down, and then they slow down on the way up. So that means at the bottom, they've reached their maximum speed. And so at that instant, they're not speeding up or slowing down. Okay, this is a pretty common type of question they would give you on the AP test, one of these vertical circle kind of things. And they like to ask about generally 3 different spots. So let me show you those spots just so you're aware. Okay, so let's say we have like a ball, like a baseball on the end of a string, and you're just zipping it around in a circle, okay? Now, when you do this, gravity is going to be pulling it down, right? And so I think this is a little blurry. Hang on. There we go. So gravity's pulling it down.
There you
go. Okay. So when it's over here, you're going to have a tension from the string, and you're going to have gravity this way, right? When you're at the top, you're going to have tension down, and you're going to have gravity down. Okay. And when you're at the bottom, you're going to have tension up, and you're going to have gravity down. Okay. They generally will ask about these 3 particular spots. So at the top, notice, remember Newton's second law, F equals ma. So if there's a net force downward, there has to be an acceleration downward. So in this case, you're accelerating down, and that makes sense because you're accelerating towards the center of the circle. That makes total sense. Okay. If, on the other hand, at the side, you have gravity down and you have tension to the left, these 2 forces would add up to be this direction, and you would have a net force in this direction. Now, what does that mean? Well, you're changing direction. Okay, so you have a centripetal acceleration this way. You have a gravity force down this way. So if you're coming around this way, you would be speeding up. Okay, so you have a tangential acceleration down, and you would have a centripetal acceleration towards the center for a net acceleration in this direction. Okay, so you'd be speeding up and turning. Here at the bottom, you're going to have, looks like these 2 forces could cancel. All right, but the thing is that you're turning, right? Notice you're not speeding up or slowing down because the forces are only vertical. But you're turning, so there has to be a net force towards the center. So what you end up with is the tension force has to be greater than mg. So you're accelerating up, okay, towards the center, and those would be centripetal accelerations. Okay? They tend to ask about those 3 spots. All right. So right here, this girl in the swing is at the bottom of that swing. And so she's accelerating straight up, C. All right. How about this one? So Ladybug is on a disc that is spinning at a constant rate. So I've drawn a 3D picture here, or I've pirated a 3D picture here. Which way is the Ladybug accelerating? All right. We have nearly complete consensus. So is the ladybug changing speed? The answer is no, because she's going around at a constant rate. So there's no tangential acceleration. If she was speeding up, if it was getting faster and faster, then she'd have an acceleration in the B direction. If the disk was slowing down, she would have an acceleration in the D direction. But because she's turning, she certainly has an acceleration in the A direction. So that's the only one we have. So the acceleration is in the A direction. Perfect. All right. Now, here's the thing. On the AP test, when you have circular motion, there's kind of a progression to understand or to be able to understand the questions. The first thing you have to do is decide, is it accelerating? Changing speed, changing direction. Second thing is what is that direction of that acceleration? And then the third thing is, well, what is the force that's causing us to go in a circle or to turn? And I want you to avoid never, ever, ever on the AP test on like a free body diagram, never call it the centripetal force, okay? Because it's really not this. The centripetal force is not a magical new force. Like in this particular one here, the planet Earth is going around the sun, and you look at it and go, hey, what's causing it to go in a circle? The centripetal force. You won't get credit because that's not the real force. That's just the name that we call these forces that cause something to go in a circle. So they want you to identify the actual real force, okay? All right. Wait a minute. Tension. Man, somebody better not cut that big spring that connects the sun to the earth, or otherwise we're in trouble. So we got to figure out what force it is. So here we go. So here are the four major forces that we see all the time in mechanics. Gravity, friction, normal force, tension. Okay, remember gravity is between two objects. Remember that friction, you have to touch the surface and try to slide or be sliding. Remember normal force, you have to touch the surface and the surface pushes back. And remember tension, there has to be a string or a rope or something that's being stretched and it's pulling on the object backwards, okay? All right, in this particular case, the force that causes the Earth to go in a circle is gravity. Okay, how about this one? We got a car making a left turn on a flat road. Which force is it that causes the car to go in a circle? So we're looking at the top view of the car. We're looking down on it from a plane. Okay, well, we've got several different answers. So let me draw a couple of free body diagrams of this so we can see it, okay? So if we look at this from the top, here's the car and here's the road, and it's going around this way. We're looking at it from the top. Then what forces do we have acting on the car? Well, there would be a gravity force, but it would be straight down. We would have a normal force, but it would be straight up. And then we would have something has to be pulling it around the turn, and that would be friction. If you don't believe that, the next time you guys have a ice storm in your area, once you get out in your car, get it up to about 60 miles an hour, and then yank the wheel to the left, and then tell me what force is it that I needed to make that turn. And it'll be friction because you just don't have any. If we look at the car from the back.
Vance, Kentucky does not endorse this.
Yeah, we'll do this as a mind experiment, not a real experiment. Having done this accidentally before in my lifetime, it's kind of frightening. So if we look at the car from the back, so this is my attempt at the car here, and here are the tires back here. So this is the back end. So you can see that gravity would pull it down, that the normal force would push it up, and that friction would be to the left, pulling it around the turn. Okay, there's no rope, so there can't be any tension. There's no like a cable or anything. And so that is my friction force because the center of the circle is over here. Okay. All right, how about this one? I don't know if you've ever been on a ride like this. This ride came out, I don't remember when, like in the 50s, I think. It's the one where we have it at the state fair here. And it's the ride where it's a big drum and you get in the drum and the drum starts spinning and then you're standing against the wall and you get stuck to the wall and the floor drops out. So you're stuck to the wall with the floor way below you. Okay. So what's the force that's causing you to go in a circle? Okay. What's the centripetal force? All right. You are correct. It is the normal force. So if here's the drum and it's spinning around like this, and here's the person here, then the normal force will be pushing them towards the center. There'll be a gravity force pulling them down the wall. So therefore, you must have enough friction to keep them from sliding down the wall. And this friction force has to equal the gravity force, or otherwise you'll slide down. Okay? So the normal force is pointing towards the center. That's our centripetal force. Okay? All right, we're back to Texas Motor Speedway. And we're talking about the bank turn. Let's talk about the bank turn over here on the far left. There's a picture of the vehicle in its banked turn. So we're looking at the front of the vehicle, and the vehicle is coming towards us. Okay, which or what is the centripetal force? Is it gravity, friction, normal force, tension, or is it a component of one of those forces, or is it a combination of multiple forces? Yeah, let me relaunch this poll here. There you go. All right, this one's a little more challenging. Let me show it to you. So, what are the forces acting on the car? Well, there would be a gravity force straight down, always straight down. On Earth, we're not getting away from gravity, always straight down. The surface is tilted, so the normal force is perpendicular. So that's going to be this way, normal. And then if there's friction, okay, so this is the tricky part about this one, if there's friction or not, okay? Turns out that there is a Goldilocks speed that if you go just at that perfect speed, they don't need any friction. Okay, so let's talk about that one first. All right. So if you're going at the magical Goldilocks speed, it's called the design speed of the turn, then these are the only forces that are necessary. Now look, the center of the turn is over here. So that means gravity cannot be the force causing us to make this turn. It has to be just a component of the normal force. Just this horizontal component is pushing us towards the center. All right. Now, all of you probably, you're all drivers probably now, and all of you probably learned that if you take a turn too fast, you start to slide out of the turn. So if this car is going too fast, it'll want to slide up the hill or out of the turn, okay? In that case, you would need friction this way in order to make the turn, all right? And so part of friction, the horizontal part of friction would be pushing you towards the center, okay? If you're going too slow, like say you're sitting on this this turn and you're not moving, like you just parked the car. If you just park the car, then it's like if the car would want to slide down the incline, right? And so friction would be in the opposite direction. Okay. So on the test, most of the questions, if they're an inclined turn like this, a bank turn, they will tell you that it's going around the turn with no need for friction. So you just don't have friction in there. Okay. And so it would just be part of the normal force. If you're going too fast, then friction and normal force are making you make the turn. Okay. All right. Okay, how about this one? This is our girl on the swing again. She's at the bottom of the swing. Okay, what's the centripetal force? Is it gravity, tension, normal, I just said all those. Tension or combination of the forces or component? Lou, I'm going to relaunch this poll here. There you go.
Sounds good. There you go. Just don't forget to share the results. I've been doing it when I can, but I'm setting up the polls for the next hour.
Okay, no worries.
Time here.
Okay. So let's take a look at our forces in this situation. So here's our kid going around on the swing, okay? And what are the forces acting on our kid? Well, there's definitely gravity, there's definitely tension, and no friction. They're not sliding across anything. No normal force because they're not touching anything. And they're directly at the bottom. So these two forces are fighting each other, and the center of the circle is up here. So that means tension has to be greater than mg. So our centripetal force would be tension minus mg. Okay? This one up minus that one down. So a combination of more than one force is our centripetal force. Okay? How about this one? We've got a roller coaster going over the top of the hill again. Okay, so now before you answer the poll, you should really always sketch a little free body diagram. Okay, ask yourself, you know, what are the forces? And then, is it accelerating? If so, which way? And that'll help you identify what the centripetal force is. All right, so let's take a look at this situation. So definitely gravity down, definitely normal force up, you know, there could be friction, you know, maybe there's friction one way or the other. But the thing is it's going around a turn. Here's the center of the circle. Gravity is definitely pulling it down that way, but the normal force is up. So these two combined are our centripetal force. Our centripetal force are some of the forces towards the center of the circle is mg minus the normal force. So that's our centripetal force. Okay, combination of those two, in this case, not really working together, fighting each other. Okay? Just like we had these two fighting over here. Okay, now this one takes a little more setup. You have a Ferris wheel. Ferris wheel is moving around at a constant rotational rate. You have a physics book sitting on a seat in the car located right here on the x-axis. So a physics book is just sitting there on the seat. Okay, and it's moving around at a constant rate. Okay, now draw your free body diagram of just the physics book. What are the forces acting on the physics book that's sitting on the seat? And then, is it accelerating? It's definitely going around the circle. So what would be the force causing it to go around in that circle at that instant? Okay, this one is kind of right off of the test from just, shoot, it wasn't last year. I think it was the year before. So when you have this Ferris wheel, and here is the seat, right? It's sitting right in here, and it's at that side. Okay, so what are the forces acting on it? Well, there's certainly going to be gravity. There's certainly going to be a normal force. Okay, but it's moving at a constant rotational rate. That means its speed is constant. Okay, but it's changing direction. So that means it has to be accelerating towards the center. So that means I need a force. My center of my circle is over here somewhere. So I need a force to the left. Well, it can't be normal. It can't be gravity. So what's the most reasonable one? It's got to be, there's no rope attached to it or string. So the reasonable thing, since it sits on a seat, oops, I wrote the wrong one, is friction. Okay? So friction is the one that's causing the book to move to the left, accelerate to the left. Okay? Yeah, and this one I think was right off of the AP test just a couple of years ago. Okay, so now on the AP test, they like to ask you questions about, you know, comparing the size of different forces. So let me give you a couple examples here. In this particular one, a ball is spun around the end of a string in what's called a conical pendulum because it makes a cone shape, okay? So this ball's going around like this, and there's a gravity force down, there's a tension force up at this angle, okay? And this angle here is the same as the angle listed here. And so now the question is which force is bigger? Tension, gravity, they're both the same, or we can't decide. All right, tension wins out and is bigger because it has to do a couple of things. So here's this ball, there's tension this way, and there's a gravity force this way. Now, these two forces cannot cancel, so we know it has to be accelerating, all right? Just from our picture here, the only way that two forces can cancel is if they're exactly equal and opposite, like say these, right? They cancel. But these two are off at angles, so they can't cancel. So the ball has to be accelerating. And since it's changing direction, we know it must be accelerating to the right, okay? So that means the up and down force has to cancel. That means this has to cancel that because it's not accelerating up and down, it's accelerating to the right. So this part of the tension, the X part of the tension to the right, is accelerating it. So therefore, tension has to be bigger. Okay? How about this one? You got a bucket of water and you're spinning it around in a vertical circle, but the water does not fall out of the bucket. So you're spinning it around like this, okay? And the question is which is bigger, gravity, tension, or they're both the same, or we don't have enough information?
Sorry, wrong hole.
Oh, there you go.
Here we go. I got the right pole up there. And that's a tension in the guy's arm, right?
Yeah. If you're talking about the water itself, then you would talk about gravity on the water and normal force on the water, right?
Mm-hmm.
Okay. So let's see. So you have this bucket up here.
That's a tough one.
This is a tough one. And they throw some of these on the test. So that's why I gave you one. So there's a tension force down and there is a gravity force down. And we know that it has to be accelerating down. It's going through an arc, so it must be accelerating down. The question is how do I compare these? I know these two add up to be my centripetal force down, but I actually don't have enough information. So the sum of the forces equal ma. We know this to be true. And since we're going around in a circle, we know that these two add up to cause us to go around in the circle. And we know that this equals v squared over r. And that's as much as we know. So depends on the speed. If the velocity is low, then you don't need a lot of tension. If the velocity is really high, the tension has to get really big because gravity is set by the mass of the object and the earth. Okay? So this is a hard one. The answer is we really don't know which one's bigger. We just know they add up to cause it to accelerate down. So that's a tricky question. Okay, how about this one? This one we know. The answer is not D. So a roller coaster is going around and it's at the very bottom of this hill. All right, let's get rid of that hole. And let me start up.
I think it's launched already.
Is it? I don't see it.
No.
I see the one with gravity and tension.
Sorry, I'll have it. I'll get it. I've got the one with gravity and normal force right
There you go.
there. Sorry. It's like a tough one.
Okay, which way is it accelerating? You have to have a net force in the direction you're accelerating. All right, let's see. We're at the bottom of this hill. When we're at the bottom of the hill, we're changing directions. So we know that we're accelerating up towards the center of the circle, okay? And so gravity force is down and the normal force is up. But since we have to be accelerating up, that means normal force has to be bigger than gravity, okay? If they were the same size, then the roller coaster car, look, if this is the same size, then these two forces cancel, and this roller coaster car would continue to go straight at a constant velocity, which we really don't want to do on a roller coaster, because then we would like crash through the tracks here. All right? So it can't be the same. Okay, here, let me share with you one of the colossal failures of my students. This was on a test. So the test was, you have a pendulum.
We have a chat question.
Oh, yeah. What you got? Hang on, let me see. I thought normal force could never exceed gravity. That's actually incorrect. Let me show you an example. That's a great question. So here is a person in an elevator.
Elevator accelerating upward.
Yeah, person in an elevator. What are the forces acting on the person? Well, there is a normal force up and there's a gravity force down. But if you press the up button and you start to accelerate up, then the normal force has to be bigger than the gravity force so that you can accelerate upward. And then when you get near the top, the floor that you want to get to, you start to accelerate down, so you slow down. So like your velocity's up, you have a positive velocity but a negative acceleration, so you slow down to a stop. When you're up here, then the gravity force is bigger than the normal force. That accounts for why you feel funky when you first hit the up button and you accelerate up, you feel heavier. That's because the normal force is bigger than gravity. And then when you get near the top and it slows down, you feel that sometimes you feel kind of a butterfly feeling in your stomach. That's because you're accelerating down and the normal force is less than gravity, okay? So normal force just depends on whether you're accelerating up or down. Let me see, another example of where normal force would be bigger than gravity is to say that the gravity force is down on a box is sitting here, and then the normal force is up. But let's say that you're pushing it this way, okay? So part of your force is down and part of your force is to the right. Well, you're pushing it down, gravity's down, so the normal force has to be bigger than gravity because it has to equal gravity plus how much you're pushing it down, okay? All right, and okay, I get this question sometimes from students. The students will say, but how does normal force know how big to be? Like, how does tension know how big to pull? And it all goes back to, if you think of an object being made of atoms, okay? So say you get an object made of atoms here, and they're connected in my simple model by springs, okay? Now, in the real world, they're connected by the bonding between the atoms, okay? And so these bonds have a certain length, a certain preferred spot, if you will, a minimum energy location, okay? So if I push down this way, I compress the atomic structure. And so what happens is they don't want to be in that location. And so they push back with a repulsive force, and that repulsive force is the normal force. So when they're smashed down, the normal force pushes back up. The atoms are just trying to get back to their preferred location, if you will. Okay, And so the more I push it down, the more it pushes back. Okay? So that's how the ground knows to push up on you when you step on the ground. When you step on the ground, you compress the atomic structure, and the atomic structure tries to snap back to its original position. So the more you push down, the more it pushes back until the floor breaks, right? As long as the floor is sturdy enough, it won't break, and you just keep pushing up. All right? Okay, does that answer your question?
Chris, I might. I think,
what, Lou?
You can also do the experiment of, doing a standing high jump while from a bathroom scale.
Oh, yeah.
And as you're accelerating upward, you'll find that the scale will read a lot more than your weight. We're about at 11 o'clock now, Chris, so I think this has been great. And I think I've got the polls set up for our next hour, but should we take a 5-minute break and convene?
Yeah, let me just quit here by asking, do you all have any questions about what we covered? Some of it's kind of tricky, right? And so that's why I wanted to kind of go through the basics, because they tend to ask a lot of these questions on the test. All right. If there are no questions, then we're going to move on to energy and work. And so let's take a 5-minute break. So it looks like we're almost at 10. So why don't we come back? I'm sorry, 10, 11 your time zone. So it looks like we're just about at 11. So why don't we come back at 11:05? And I'll see you then.
All right, welcome back.
Okay.
And now we're ready to start our second hour.
All right, welcome back, everybody. I hope you're all there. We're going to talk about work and energy. So the first part of this little presentation, I'm just going to kind of go through everything because work and energy sometimes feels a little different than, say, talking about kinematics or forces or momentum, because they're all vector concepts. They all have a direction. Whereas work and energy are scalar concepts, meaning that they're just a quantity. They're just a number that describes the state that the situation is in, okay, or that the system is in. So we have to kind of think about, excuse me, work and energy a little differently. So all we're trying to do really is just to figure out the system right now at this state, at this location. How much energy does it have? And then at state number 2, how much energy does it have? And did it change going from state 1 to state 2? That's really it. So here we go. So first thing, you have to remember that they're going to say words like system. And a system is just a collection of objects that you're considering together. It's very important that you know what system you're working with, okay? So work is the method for which we transfer, transfer energy from one object to another, or from the outside environment into our system or out of our system, okay? So I know probably when you were younger, science teachers would tell you energy is always conserved. Now, in the biggest picture, that's a good thing to say. But when we're talking about, say, like a baseball or a car, or just think about you, your energy state can change as the day goes on, depending on your interaction with the environment, everything on the outside. So like at lunch, you're going to add energy to your system by eating chemical potential energy called food, all right? So when we're talking about mechanics, the same thing is true. You have an object or several objects you're considering as your system, and you got to decide whether the outside environment is adding energy into or taking energy out of your system that you're defining. It doesn't mean that energy is not conserved. It just means for our system that we're looking at, did the energy go up for that system or did it not? Okay. So work is our way that we can transfer energy into or out of our system. And work is the external force. That's important. Forces from the outside acting through a displacement, and we have this angle here. Okay, remember when the angle is 90 degrees between the force and the displacement, there is no work done. Okay, if there is no displacement, there is no work done. So like if I stand up and push against the wall here for 10 minutes, I'll do no work because even though I'm applying a force to it, it didn't displace. Okay, another example of when you don't get any work is things like, here it is, like this. Say you got a car that gravity force is down and the normal force is up, okay? And say it's displacing to the right. Now look, this force is perpendicular to that. So the cosine theta between those two is the cosine of 90. So it's 0. So the gravity force doesn't do any work. And the normal force is likewise not doing any work. So in the absence of any other forces, no work is being done. So the car will continue to roll in the same energy state with the same kinetic energy, in theory, forever. Now, how is that different than when we have an object on an incline? Okay, when we have a car on an incline, notice that the gravity force is down and the normal force is up. Well, perpendicular to the surface. Okay, notice that we are displacing if it rolls down the hill like this. Now, think about it for a second. The normal force is still perpendicular to the displacement. So the work done by the normal force has to be 0. It's not making the car speed up. It's not giving the car any energy. However, notice this angle here is less than 90. So therefore, the part of the gravity force, at least, is causing us to displace. And so the work done by gravity will be positive, and that will increase the energy of the car. Okay? So when you think about energy, think about it kind of like money or accounting. You know, the car has a certain amount of money or energy, okay? And then the gravity force added money or energy into the system, so now the car has more money or energy, okay? And so that's how we need to think about this concept of work and energy, is that it's just a number that tells us something about the system, okay? Work also equals the change in the energy of the system. So this is the way that I tell my students to write conservation of energy. I tell them that the energy you start with, situation 1 for the system, plus any work done by external forces on the system will equal the energy of the system at the end, okay? So the energy at the beginning and the end only equal each other if there's no work done. And one last thing, you can find work by finding the area of a force displacement graph. It's this area underneath the curve. If you're in calculus, that's called the integral. If you're not in calculus, it's called the area of the curve. Anytime you see a force displacement graph, your little light bulb should go off above your head going, ooh, work. I can find work from this graph, okay? And that means it's probably related to energy in the problem. Okay, what types of energies do we have? We have 2 types of kinetic energy. There's translational kinetic energy and rotational kinetic energy. Now, the AP test and physics books, they just call this energy. They say they just call it kinetic energy. So you have to decide, is it moving from place to place, then it has translational kinetic energy. Is it spinning? It'll have rotational kinetic energy. Now, your teacher and you may not have gotten to rotational kinetic energy yet in your class. That's okay. I'll just give you a little heads up on it before you get there. So when you get there, it's no big deal. Oops, I did the wrong thing again. Here it is. So So like a tire that's rolling, omega, and moving, velocity, it will have both a kinetic translational 1/2 mv squared because it's physically, its center of mass is physically moving from place to place, okay? But it's also spinning, so it'll have kinetic energy rotational, which is 1/2 I omega squared. Now, if you haven't gotten there yet, your teacher will tell you what these two things mean, okay? Just think of it this way. Notice how these two equations are very similar. So this V is translational velocity, moving from place to place. This omega is rotational velocity. It just tells you how quickly you're spinning. And this M is your inertia, okay? This I is your rotational inertia. It just tells you how hard it is for you to start something spinning or slow something that's spinning, stop it from spinning, like slow it down, okay? So this M and I are the inertia, and these are how fast. Okay, how fast is it moving? What's its inertia? How fast is it spinning? What's its rotational inertia? Okay, so if you haven't gotten there yet, don't worry. It's on your test, but you have plenty of time to get there. Okay, let's see here. Let me go back. All right, so here's a key thing. What do you need in order to have kinetic energy? The system has to be the object, okay? So like if I say, what's the energy of this car? The system is the car, okay? Then that's all you need, all right? And kinetic energy can only be positive. I'm sorry, 0 or positive. If it's not moving, it has 0 kinetic energy. If it's not rolling or rotating, it has no rotational kinetic energy. Okay, there's no negative kinetic energy. All right, gravitational potential energy comes in 2 varieties. There's the general form down here at the bottom. This is the one we use when we have planets. This has showed up on the test occasionally. I'll work a little problem out with the one on the bottom so that you can see that it's not a big deal, all right? And then the one on the top is the one you've seen before. It's the changing kinetic energy equals mg delta y. Now, in order to have gravitational potential energy, you have to have the Earth and the object in your system, okay? If you don't have the Earth in your system, you cannot have gravitational potential energy. Okay, so like, let's say a skydiver is falling. If the skydiver is falling and your system is just the skydiver, you can only have kinetic energy. If you have a skydiver and the Earth as your system, then you'll have gravitational potential energy and kinetic energy. Okay, it's a matter of accounting on how you're handling the gravitational force, okay? Gravitational potential energy can be negative if you put the 0 spot, up a little higher and it goes below that spot, okay? Most of the time we try to pick the 0 spot at the lowest points. We don't deal with any zeros. Let me show you this general form because it does show up occasionally on the test. So let's say we have an object here. Let's call it mass m. We have an object here. We'll call it 2m. And we have an object here that's 3m, okay? And they want to know what's the gravitational potential energy for the system that includes all 3, all right? So our equation for it is this. Actually, they usually write big G here. It's negative G M1 M2 over R. Okay, so let's call this a nice equilateral triangle to make it simple. We'll call that X and X and X. Okay? All right, I want you to notice that this equation only has 2 masses in it. So that means I have to handle these two at a time. So I'm going to first handle this orange pair. So that means the gravitational potential energy between these two would be negative G m times 3m over x, okay? Which gives me a total of 3 gm squared over x, and that's negative, okay? So now I'm going to handle this pair, the green pair. The green pair would be negative G 3m times 2m over x. So a grand total of negative 6 gm squared over x. Okay? And then we're going to do this blue pair up here. This blue pair would be negative g m times 2m over x, which would be negative 2 gm squared over x. And now all I have to do is add them all up. Okay? So when I add them all up, I've got 6, 7, 8, 9, 10, 11. So I'd have negative 11 gm squared over x. This is the energy of the entire system. Okay? Just making sure I did my math correctly. Yep. All right? So that's all you'd have to do. Is just take each pair one at a time, find each pair, and then add them all up. Okay? Piece of cake. When do we use this one? We use this one when we can't use this one. So when can we not use this one? Whenever we don't have G being constant. G is constant. G must be constant. If it's not constant, like for instance, these are just masses, I don't know what the acceleration due to gravity is between these masses. I don't know what it is. So I cannot use this equation. Or another example would be, here's the Earth, and here's a person way out here. When they're way out here, this G right here, what is it? I don't know. I know what then when I'm near the Earth, that G equals 9.8. But when I'm way out here, I don't know what G is. So I can't use this one because G has to be that constant that we know, 9.8. All right? So for an astronaut floating around way up here in space, I would have to use this one. For a person near the Earth's surface, whereas G equals 9.8, I'm going to use the simple one. Does that make sense? So we try to use the simple one when we can, because it's easier. All right, and then we have elastic or spring potential energy. It's 1/2 kx squared. Now, in order to have spring potential energy, you have to have a spring in your system. Okay, so it has to be object plus spring. The x is the stretch or compression of the spring or object, and when you calculate it, it's always going to be either 0 or positive, just like kinetic energy, because of the x squared. All right? So here's the deal. Total mechanical energy of the system. It depends on the system you choose, okay? If you have an Earth object spring system, then you could have both kinds of kinetic, gravitational, and spring. But if you have only the object as your system, then you can only have kinetic energy. That's important, okay? So when they ask a question, they'll tell you in the problem, like if they want you to consider a certain system, like they want you to consider, you know, the Earth roller coaster car system. Okay, so then you know, hey, Earth roller coaster. So I'm considering the kinetic energy of the roller coaster and the gravitational potential energy between the Earth and the roller coaster. Okay? So look for the wording. Make sure the wording tells you what kind of energy to consider. And then our last equation is power. And power just tells us the rate at which work is done. And since work is FD cosine theta, look at this. D divided by T, that's velocity. So you could write it as force times velocity times cosine theta. Or since work equals the change in energy of the system, it's just the change in energy of the system divided by time. All right, that's power. By the way, if they give you power and they give you time, you can always calculate work, right? Work equals power times time. One last thing, because they end up putting these two ideas together quite often on the test. It's the idea of momentum and energy, okay? So momentum if you consider all the objects that are interacting, okay, and there aren't any other outside forces, momentum is always conserved, okay, for objects that interact. But when objects collide, the kinetic energy is not always the same before and after, okay? If it's an elastic collision, then the initial and final kinetic energy is the same, and we say that energy is conserved in the collision. But if it's an inelastic collision, like if they stick together or they bounce, but they bounce off slower, then you've lost kinetic energy. And there's some situations where you gain kinetic energy in the collision, okay, or the interaction. Then we call those explosions. So let me give you a quick visual picture of all these. So like, say that you have a person here and a person here, and they're next to each other and they push each other off so that afterwards they both have a velocity backwards. One's backwards and one's forwards. Okay, the kinetic energy here initially was 0, but the kinetic energy here at final is greater than 0. So this is an explosion. We've gained energy, okay? Energy for the system has gone up because work was done, all right? And then we have the situation, say like they do this a lot, where you have an object here that's moving along and it hits another object, and this object was at rest, and after the collision, they're stuck together, okay? Anytime this happens, so V1 and this is V2, anytime this happens, this is a perfectly inelastic collision. And what happens here is the kinetic energy initially is greater than the kinetic energy final. You've lost kinetic energy. Okay, so you need to be aware of this, that in this collision, energy is not conserved. And in this collision, energy is not conserved. Okay, at least mechanical energy is not conserved. Okay. So just be careful of that. The only time that we can say the kinetic energy initial equals the kinetic energy final in a collision is if it's an elastic collision. So look for that word. If they say it's elastic, then this is true. Okay? If it's not elastic, then the energy is not the same before and after. Okay, so let's practice this a little bit. Let's make sure we understand which forces are doing work and which ones are not. So take a look at this figure. In the figure below, we have all of these boxes are identical. They're all 10-kilogram boxes. And they're moving at the same initial velocity to the right. So they're all moving to the right on a flat surface. The same magnitude force, F, is applied to each box through the distance that's indicated, okay? And we want to know, rank the work done on the box by F as it moves the distance that's shown, okay? So what I'd like for you to do is to type in the chat what you think the ranking should be. Okay? Okay, we're going to rank from greatest to least. As a hint, which forces aren't doing any work, which ones are doing positive work, which ones are doing negative work. All right, let's see. Okay, I see quite a few comments in here. So first of all, if we identify our work or forces that aren't doing any work, D and F aren't doing any work, okay? So the forces are perpendicular to the way it's moving, so no work done. And then E is negative work, so that one's going to be the smallest. And then let's see, A and B are in the direction we're going, but B, it moves farther, so B is the most work, A is next, and then C is positive, but the force is at an angle. And then D and F are both 0, and then E is the worst. Not the worst, the least, okay? So keep an eye on those angles, right? That helps us figure out whether it's positive, negative, or 0. Okay, how about this one? Cars that are moving along horizontal roads are going to be stopped by plowing into identical barriers. By the way, I don't encourage this. But if in an emergency, you're going to plow into these barriers, all the cars have the same size and shape, but some are carrying loads with different masses. All the cars are going to be stopped by the same constant force. So these barriers are made to supply a constant force, and it's the same force in each case. It doesn't matter how fast you hit them, the force is the same. Okay, rank the distance that is needed to stop the cars with the same force. All right, let's see here. Okay. Let's see. Hey, we're doing great. I think we have quite a few correct answers. So the deal is this. Let me show you a little bit of math so we can tie this to math. So here at the bottom, the car has kinetic energy. Now, I shouldn't really put an arrow to designate kinetic energy. It has a velocity to the right, and so therefore it has kinetic energy. The barrels are going to exert a force to the left. Okay, so here, energy you start with plus the work done equals the energy you end with for our car. The car starts with kinetic energy. There's negative work done by the barrier because the barrier is pushing the opposite direction it's going to displace. And we're going to end up with no energy because it's going to stop. So that means kinetic energy minus FD, the work done by the barrier, equals 0, or kinetic energy equals FD. But since F is the same for each one, then the kinetic energy is proportional to the distance. So all we care about is which one has the most kinetic energy. That's going to be the hardest one to stop, and it's going to go the farthest. So I have B, and then C, and then D, and then A. I think in your head, you can probably easily calculate that B is greater than C. And then after that, you might need a calculator, but there we go. All right, how about this one? In each case below, a toboggan, for those of you that have grown up in the South, a toboggan is like a sled with no runners, okay? Starts from rest and slides without friction down a snowy hill. The toboggans are all identical, and the starting heights, the vertical distance above the flat bottom of the incline, and the angles of the hills are given. Rank the speed of the toboggans at the bottom of the incline. Okay. Now, some of you are going to be more comfortable with forces and with kinematics and things like that, and you're not as comfortable with energy. But I want to encourage you that energy, if you can solve it with energy, then energy is always, almost always, the easiest way to solve a problem because there's no vectors involved, and so the math is simpler. So anytime you have an object that's changing height, you know you have a change in potential energy, okay? And if it's moving, you have kinetic energy, all right? So for our toboggan Earth system, the toboggan starts with potential energy, and at the bottom it ends with kinetic energy. And the really cool thing about this problem is that if you handle it with energy, you don't care about the angle. The angle makes no difference whatsoever as far as energy is concerned. All you care about is the vertical height. So it makes things simpler, okay? So like for instance, look at A and B. Almost everybody is tempted to say, hey, look, they're starting from the same height, but A is steeper, so it's going to be faster at the bottom. But it won't be. If you go through all the forces and do kinematics, you'll find that A has a larger acceleration, but because it's steeper, it has a shorter slope to go down. So therefore, even though it has a higher acceleration, it accelerates over a shorter distance and time, so its velocity is no higher than B's, okay? So A and B will be identically the same. Okay, and energy, you can see it real easy. Hey, they have the same gravitational potential energy to start, and they're going to the same height at the bottom, so therefore they must be the same speed at the bottom. Okay, so it should be A equals B greater than D, and C is the least. Okay? All right. I'm going to skip this one because we're already at 10:39. Let's go to this one. This is a great one. What we have here is we have an archer at the top of a building shooting arrows, which I wouldn't encourage in the city. You'll probably get arrested. So you're at the top of a building shooting arrows. Every arrow is shot at the same initial velocity. Some of the arrows are shot downward at a 45-degree angle. Some are shot upward at a 45-degree angle. Some are shot horizontally, but they all have the same initial velocity, and they're all going to fall or fly through the air and hit the ground. Question is, rank the speed of the arrows just before they hit the ground. So which ones are going to hit the ground with the biggest velocity and which ones with the smallest velocity? Rank it from greatest to least. And if you think about it in terms of energy, because we have change in height and we have kinetic energy because we have motion, it's a lot easier to figure out.
And Chris?
Yes, sir.
Not to be pedantic, but I think you mean same speed, because they can't have the same velocity if they're pointing in different directions.
Oh, somebody just made fun of me. Yes, they have the same speed because they won't have the same direction when they hit the ground because they're going to go through a parabolic arc. That's correct.
I know you were making that a trick question for me.
Man, it's going to dock my pay. All right, here we go. So all of the arrows start at the top of the building. So energy at the top of the building plus any work done equals energy at the bottom when it hits the ground. Now we're going to do arrow plus earth system. Okay. Now, what are the forces acting on the arrow when it's flying through the air? There's just gravity, right? Gravity is part of our internal to our system. So here's our system. Gravity is internal, so it's not going to do any work. There are no other forces. So therefore, the work will be zero, okay? Zero. So it starts at the top of the building moving, and it's above the ground. And when it gets to the ground at the bottom, it's going to have no potential left because I assume we're all going to put the ground as zero. So that means, wait a minute, they all start with the same kinetic energy at the top. They're all shot at the same speed. So the ones at the bottom will be going the fastest whenever they started the highest up. So that means C and E will hit the ground at the same speed. Now, will they hit the same spot? No. Will they stay in the air the same amount of time? No, because C is going to go way up and then come down. But will they hit with the same speed? The answer is yes, same kinetic energy. In fact, if you think about it, you can draw like a little parabolic arc here from C to E. If you think about it, in a parabolic trajectory, the arrow will start here at C, it'll end up here at E, and then be identical from there down to the ground. All right? So it just takes longer for it to get to that spot. So C and E will have the highest kinetic energy at the bottom. A will be next, and then D and E both start at the same height, same kinetic energy, so they're going to hit the ground with the slowest speed. That'll be equal. All right? So CE greater than A, and then B equals D. All right? I love that problem because it makes you think. Okay, Jason and Brent race up a hill that is 30 meters high. Jason takes the path that is 60 meters, while Brent takes a longer path that's 100 meters. It takes Jason 40 seconds, while Brent runs up his path for a shorter time of 30 seconds. They both start from rest at the same height and stop at the top. Also, they have the same weight. Okay? Is the work that Jason does going up the hill greater than, less than, the same as the work done by Brent going up the same hill? Okay. Now remember, there's several ways to find work. You can think of work as force times distance. You can think of work as the change in energy. Okay, since it might be hard for me to figure out the force times distance and the cosine theta, it might be easiest for us to just think of what kind of energy are they changing, all right? So they're starting down here, and they all both end up here at rest. So they're going to end up with the same gravitational potential energy. That means if they end up with the same gravitational potential energy, that means they would have done the same amount of work. Because they change the potential energy exactly the same amount. All right, so that's identical. However, what about the power? Well, it looks like Brent gets up there first, so he does his work in less amount of time. So Brent will have more power or generate more power than Jason does. Okay, does that make sense? All right, any questions on that one? Okay, then let's go on to our next one. Okay, I hope your teacher has been using energy bar charts with you. It's you're likely to see these on the test, at least in some form or another. And they help you understand what's going on. So what an energy bar chart is all you have to do is you just have to draw a little bar here to represent how much kinetic, gravitational potential, or spring potential energy you have. So this is the initial energy, and this is the work being done, and then this is the final energy of the system, okay? So in this particular case, you have this performer on a skateboard, and they are launched by this spring. So the spring is initially compressed at distance delta x, and then his speed on the horizontal portion of the ramp is v. So you push this guy against here, and then you launch him, okay? So what we want to know is what is the initial energy of the system of the Earth skateboarder spring system? Okay, so that means Earth, we can have gravitational potential energy. Spring, we can have spring potential energy. And skateboarder, we can have kinetic energy. Okay? When we start from rest, we compressed against the spring until we see him in this position here launched. All right? So, what kind of energy does the skateboarder start with? Well, they start with 0 kinetic. So they're way down here, 0. Okay? And then they're on the ground. So 0 gravitational potential energy, right? Down here. But they are compressed against the spring. So how much? Well, I'm just going to draw this much. Okay? So here's my bar right here. So they start with spring potential energy. Okay? Now let's think about work done. So what are the forces acting on the skateboarder? Well, the skateboarder has a gravity force down, they have a normal force up, okay? And then they did have this spring force on them, right? Force from the spring. And here's normal. And then here's gravity. Okay. Now, gravity force doesn't do any work because it's internal to our skateboarder earth system. So it's internal, so no work. Normal force doesn't do any work because we're moving to the right and that's perpendicular, so no work. Spring doesn't do any work because it's part of our system, so no work. So that means the work is 0, okay? So that means at the end, what do we have for kinetic energy? Our kinetic energy at the end has to equal exactly the same as our spring potential energy we started with. Okay, so it's going to look like that. All right, so spring potential turns into kinetic energy. No work done. Okay? All right, here's a harder one. You have a 100 Newton box that's initially 1 meter above the ground while it's moving upward at 10 meters per second. So you have the disembodied hand of science here pushing this thing up with a force of 120 newtons, and it's moving, at least initially, at 10 meters per second upward. Okay? Now it says complete the energy bar chart for the Earth box system. Okay? So since we have an Earth box system, that means that we don't have any springs. So we're not going to have any spring. So I can just cross those out or just put them down here at 0. Okay? Now they tell us it begins at 500 joules of kinetic energy, and they also tell us it moves upward a distance of 1 meter. Okay? All right, so let's go through this. We have an Earth box system. What are the forces acting on this box? Well, there's the 120 newtons from the disembodied hand of science. And then there's a gravity force down. Okay? Does the gravity force do any work? Well, the answer is no, because here's the Earth down here. It's part of the Earth box system. That's internal to our system. So no work done. So only this one is doing work. That's from the hand. That's not part of our system. So how much work does the hand do? Well, it moves upward 1 meter, and that's 120 newtons. So that means force times distance. That means this should be 120. So let's see, 1, 2, 3, 4, 5. So this right here should be a little over 1. So that's 120 newtons of work. Why did I make it positive? Why didn't I make it negative? Remember that work equals force times distance times cosine theta. And since the force is up and it's displacing up, then that's going to be positive work. Okay? Now, how much gravitational potential energy did we start with? It says we're initially 1 meter above the ground, and it's a 100 Newton box. All right, so let's see. That's mgy. So 100 is mg. The y distance is 1, so that means this starts off at 100. So I'm going to write that down, 100. Okay, so that means my starting energy is 600. But I'm going to add to it 120. So my final energy must be 720. All right, well, let's see. we know that afterwards it started at 1 meter but ends 1 meter higher. So that means we're going to end up with 200 here. So how much is the kinetic energy having to be? Well, it's got to be 520, right? Okay, because the initial energy plus the work done has to equal the final energy. And there you go. Energy bar charts. Do we have any questions on this? Okay.
If you want to jump in and go ahead and unmute yourselves, we've got a small group here.
Yeah, we got a small group. Do we have any questions on how to do an energy bar chart?
Nope.
Okay.
All right.
All right, awesome. See how much time we got. Oh, let's go to, why don't we go to the last couple of multiple choice, because we're got about 5 minutes left. So here we go. Engineers are working on a new method to launch supplies to the International Space Station. This method consists of using a long cannon that shoots a capsule directly to the ISS, where it will be retrieved and the supplies unloaded from the capsule. The length of this launch cannon is x sub f, as seen in the figure. By using different propulsion fuels in the cannon, engineers can produce different force profiles on the capsule during launch, as seen in the following graphs. The maximum force in each case, F max, is the same. Which force distribution will produce the greatest velocity of the supply capsule during launch? Place your answer in the chat.
Chris, I opened up a poll for you here.
Thank you. I see it. Okay, what kind of graph is it? Always ask yourself, whenever you see a graph, look at the axis and ask yourself, what kind of graph is that? It's an F versus X, or force versus displacement or position graph. Then ask yourself, what kind of physics uses that kind of graph? And remember that the area of the graph equals the work. So which of these is going to do the most work on the capsule? Let's see. If we look at the area, where is my, here we are. So here's our area. Our area would be this, or area would be this, or area would be this, or area would be this ridiculously small thing. So D is not what we want. Actually, A and B have the exact same area. It's C that has the most area. Okay, so C is the correct answer because it does the most work. All right? Okay, let's look at our next one. We have two blocks, A and B, sit at the top of identical frictionless inclines. The mass of block A is 3 times the mass of block B. The blocks are each released from rest and slide down the incline to the bottom. These are frictionless inclines of science, okay? Which of the following correctly gives the relationship between the velocities and kinetic energies of the blocks when they reach the bottom of the incline? All right. If it's conservation of energy, the potential energy turns into kinetic. Remember, the mass is going to cancel out. Let me show you. So we have this block up here. It's coming down to here. It's going to start with gravitational potential there and kinetic here. So mgy equals 1/2 mv squared. M is going to cancel, so the mass won't matter for the velocity. So the velocities will be the same. However, the one with the more mass at the start will have more kinetic at the bottom. So the answer is velocities are the same. So it's one of these two, but the kinetic energy of A is greater than B just because it has a bigger mass. Okay? Very good. All right. And, ooh, a numerical one. Our last one. So in this particular one, you have a roller coaster. It's 80 kilograms. It's starting at the top. It's moving at 10 meters per second. It's traveling down this crest of a hill from 40 meters down to 10 meters. And the speed of the car at the bottom is 24 meters per second. The mechanical energy lost to friction is most nearly. All right, you got to do a little math on this one.
Yeah.
So on this particular one, what we're going to find is you have both kinetic and gravitational potential energy at the top. And at the bottom, you have both kinetic and gravitational potential energy at the bottom. All right, so you have to do a little bit of math to figure this one out. So you got to figure out both of them at the top, both of them at the bottom. Now, some of you will be a little sneaky, and you'll just call this 0 height here. And then so you'll make this have 30 meters of height, and this one have 0 meters of height. You can do that to simplify your math a little bit if you want. But what you end up finding is that at the top, we have 5,000, approximately 5,000 more joules at the top than we have at the bottom. So we've lost some due to frictional work in the opposite direction. So where is my, here it is. So the answer is C. Okay, very good. All right, everybody. We are out of time. And I want to thank you for showing up. I hope this has been helpful to you to kind of go over some things. Everybody have a great, great Saturday. And good luck on the AP test. I won't see you anymore. So good luck. You're going to do awesome. See ya.
Thanks so much, Chris, and all of you teachers and students participating. I'm going to cut the recording here and wish you a good Saturday. Bye-bye now.